Okay, so we're going to go through a multi-period work scheduling problem where the demand is changing over time, which influences the scheduling required. So we're starting with this is a problem in section 3.12 of the textbook, example number 16. It's about a computer service store called CSL that requires a certain number of skilled repair time per month. And it has the next skilled repair times required per month for the next 5 months. And within the problem, they mentioned that at the beginning of January, 50 skilled technicians work for CSL, and they can work a maximum of 160 hours per month. And when they prepare to increase demand for the future, they have to train new technicians. And during a new trainee first month of training, they must be supervised for 50 hours by an experienced technician, which removes time that they could be spending servicing, which would be part of these required hours. And then as far as pay goes, each experienced technician is paid $2,000 a month, even if they worked less than 160 hours. And the new trainees are paid $1,000 a month. And then at the end of every month, 5% of experienced technicians quit. So the goal of the LP is to minimize CSL's labor costs while also meeting the service requirements, which are changing for the next 5 months, as described in the beginning of the problem. Okay, so ultimately we have our decision variables. We're going to have x1 equals the number of technicians trained in months. Well, we'll just say xi, and it's in months. I equals 1, 2, 3, 4, and 5, going January through May. And then we'll have yi is the number of experienced technicians at the beginning of each month. Okay, so now we have our decision variables defined. And so now we're going into our objective function. So we want to minimize the total labor cost. So let's go into that. So objective. So the total labor cost is the cost of paying the trainees plus the cost of paying the experienced technicians. Okay. Okay. So Okay, so then basically our total labor cost in terms of x1 and xi and yi ends up being, if we're doing the trainees first, it'll be $1,000 times x1 plus x2 and then plus the $2,000 for the number of experienced workers per month. So the objective is to minimize z, where z equals this. Okay, so now we can box this in because this is the answer to our, it's not the answer, but this is part of our summary. It's our objective. Okay, so now we're going to look at the constraints that CSL is facing. Okay. So we have an initial value of 50 skilled technicians working for CSL in January. Okay, so Y1 equals 50, basically. Because this is the Y's, the number of technicians, or the number of skilled technicians at the beginning of the month. So we can go ahead and say at the beginning of Y1, at beginning of, beginning of January, we have 50 skilled workers. Okay, and then we know that the number of available technician hours during month I has to be greater than or equal to the number of technician hours required during month I. So available must be greater than or equal to required. Okay. So I can just write that out. Number available must be greater than or equal to number of required technician hours. Required and available are the important ones here. Okay, so then we can have the basically the number of available skilled hours we have during a single month. We know that that would be 160 because each experienced person is 150 for YI minus they have to train any new person for 50 hours. So that takes away from their training time. So this ends up being our constraint here. Okay, so actually that's not our constraint here. That is the number of available skilled hours. Okay, then we have the number of required hours were given to us in the beginning. So if we have for month 1, 160 y1 minus 50 x2 must be greater than or equal to 6,000. Okay, so then we'll just keep doing this. Month 2, 160 y1 minus 50 x2, 7,000 and 8,000, 9,500, and then 11,000. Okay. Okay. Okay, so these are our constraints for the number of skilled hours required and what's available. Okay, so now we need to relate the number of technicians available. Sorry, go back. Okay. Okay, so now we need constraints that relate variables from different periods, okay? And we know, like the other time scheduling problems, that the number of technicians available is dependent upon the number from the previous month. So we have experienced technicians available at the beginning of month I is equal to experienced techs available at the beginning of the last month available I minus 1 plus the technicians trained the month before, because now they are considered experienced. And then we have to subtract that 5%. So experienced techs who quit. And that's at the end of that month. Okay. So that means we already know what Y1 is because we know it's 50. So then that means for Y2 in February, that would be the number of technicians that started in January plus the number of trainees in January minus 0.05 the number of experienced technicians in year month one. Okay, so now we can keep doing this for the others. So y3 is y2 plus x2 minus 0.05 y2. Or okay, and now we know for the non-negativity, we know that everything x sub I and y sub I all must be greater than or equal to 0. We cannot have negative humans. So for I equals 1, 2, 3, 4, and 5. Okay, so now we have the following linear program. So we can this because this is what we're going to pull into our summary. Same for this. Get this guy. Okay. Start our summary with our objective. Add in things. Summary. Okay, such that, and now we go into our constraints. This y1 equals 50. And then I'll go ahead and do these next since it's more consistent. And lastly, I'll do the required hours constraint compared to available hours. Okay, slightly different sizes, but that's okay. And finally, our non-negativity constraints. Okay, and there's our final answer, final summary. Obviously, this is not the answer. This is the formulation of the linear program, but we can find the solution using Cplex, or as in the next unit, we will learn simplex. So that's it.